Thank you everyone for joining our QSR webinar. Today we have invited Professor Satish Bagapanam from Texas A&M University to speak on dealing with the streaming data for smart manufacturing. We have known Professor Satish Bagapanam for a while. He's a renowned scientist in our field. And despite so let me just briefly go over his bio so we know his research a little bit better. So Professor Satish Bagapanam is currently the Rockwell International Professor in the Department of Industrial and System Engineering at Texas A&M University. He is also the director of Texas A&M Engineering Experimentation Station Institute for Manufacturing Systems. His research in smart manufacturing addresses the harnessing of high-resolution nonlinear dynamic information, especially from wireless MEM sensors, to improve the monitoring and prognostics, mainly of ultra precision and the nano manufacturing processes and machines. And he has published over 160 peer-reviewed publications, really impressive, and 5 pending patents. He received over $6 million in grants as PI and co-PI from NSF, DOD, and the private companies. And he has over 17 best papers and poster recognitions. He's a fellow of IISE and a fellow of SME. And his work has been recognized by his previous place, Oklahoma State University, and also by Texas A&M, of course. So without further ado, let me invite Professor Bagapanam to give us talk on his research in streaming data in smart manufacturing. Okay, please. Yes, Grace, this session is recorded. Okay, please, Professor Bagapanam, you have the floor. Go ahead, please.
Lulu, thank you so much for such a kind and elaborate introduction. I will try to keep up with such wonderful remarks that you have made during the remainder of this presentation. And before I begin, I hope everybody is doing well, safe and healthy. And it's wonderful to see some of you, some of our QSR members in the screen here. And I look forward to meeting you sometime soon. And I hope all this pandemic and the trouble leave us very soon. With that note, let me begin. This is something that I have put together based on the works done by my students, Zimo, Asif, Afreen, Darpit, and Bhaskar. And what I will try to do in this presentation is not talk about solutions, but present the challenges that arise in some of the smart manufacturing contexts, and what kind of issues arise, especially when we deal with the data that occur in smart manufacturing. And I'm sure as a community, we probably have equivalent or even better solutions to these problems than what we have been able to come up with. But wherever questions get asked, I will try to answer on some of the solutions that we have come up with to addressing these problems. So let me begin by talking about smart manufacturing and what our group has been doing there. And then I will talk about 3 different problems and then deal with each one of them in some detail. And again, I'm assuming that our group has both engineering as well as statistics researchers. So I will try to match the broad interest our QSR family has on both engineering as well as data science aspects of QSR as a field. Let me begin by providing an input as to what and how I think about smart manufacturing. When we think about smart manufacturing, of course, there has been advances in manufacturing technologies that enhance our ability to create products that cannot be created before. Additive manufacturing, nano manufacturing. In fact, our QSR community has looked at several data science challenges in each of these uh, manufacturing technologies. It's not just manufacturing platforms alone. There has been a significant growth in the discovery as well as deployment of materials. And all these things happen through the advancements in what people in the general public call as AI, and we refer to as data science, and looking at advanced learning technologies as well as emerging into most of these what we call as prescriptive analytics. And in addition to that, there has been significant advances in measurement technologies, both in terms of sensors as well as communications, and also advances in computing, advanced cloud, edge, and other architectures, as well as the use of clean energy to make this manufacturing not only efficient, productive, but also sustainable. So this is a rare opportunity where all these advancements that we are seeing in various different fields can be brought in to advance the way we make things. That's pretty much how I see smart manufacturing. But in this context, there are some important points that I would like to lay to our group. The first one is it is extremely important to look into this, and I hope this presentation helps some of us to look into this problem in much more depth, and then raises the interest of this problem among our community. It contributes significant portion of our US GDP, and lots of these industrial groups are becoming part of the smart manufacturing effort. And second and more important thing is from a data science standpoint, the amount of data that gets generated in manufacturing exceeds the data that gets generated in any other field. So if someone wants to study data science approaches, manufacturing would be a very fertile field. In here, there are certain interesting challenges in that very little of the data that gets generated in this manufacturing industry is currently utilized. So there is an opportunity to harness this information in many, many different ways. These include the way we actually design and make smart products. What I have put in the screen are three different what we call as emerging products. The first one is morphing wings on the aircrafts. This is not a dream anymore. In fact, using the shape memory alloys, we can actually create some of these materials. I mean, some of the materials needed to create this morphing behavior. And second thing is a 3D printed house. We can create the kinds of house of the shapes that we cannot possibly even imagine. So, some of these advances in the 7 things that we outlined in the previous slide probably can come handy as we develop these technologies. Third picture is most on the consumer level. We can create multi-material 3D printed a single integral part. So essentially we gets tested, and the multi-material component gets printed for us on the point of use. So this is an interesting possibilities that are emerging. And alongside, we are looking at not just designing a component to meet the dimensional accuracy, but also to meet the material and microstructure. So we can actually control the product, not just to the dimensional tolerances and surfaces, morphology, but also the materials and the microstructure. So these are some emerging ideas that manufacturing community is looking at, where the idea of data science can really enhance some of the thrust that we are talking about. And the third is something that QSR community has looked into for a long time. Can we actually use the data science methods to use the data from the manufacturing process to self-correct the faults, improve the asset management, as well as optimize the machine parameters to avoid as well as overcome some of the quality issues. And people are talking about moving from flexibility to automation to autonomy. So we can actually create what are called lights off factories that are so much safer and much more reliable than the factories of today. And more than in the US, European as well as some of the Asian countries are working in a big way on this thrust of creating lights off factories. And another item that is emerging is cybersecurity. We can actually use, again, advances in data science to address security vulnerabilities in manufacturing systems. In all these applications, if you look at it in depth, the foundations are essentially looking at combination of physical science, that is manufacturing science and data science. How can we bring these knowledge components together to address some of these exciting emerging challenges? And that, in essence, is the theme that is emerging from a data science standpoint for smart manufacturing. And when we look at what has been done on data science and AI for smart manufacturing, the first thing that comes to our mind is machine learning. There has been a lot of work that our community as well as the manufacturing community has looked at in applying machine learning techniques and developing new machine learning techniques to address manufacturing challenges. And in essence, what we are trying to do is to develop and basically identify the function that maps certain inputs to certain outputs. That's pretty much what all these deep learning methods do. And there have been, in my view, proliferation of approaches, especially from our community and beyond, to address many manufacturing related challenges through advancements in machine learning, as well as AI methods. But that is just one component of where data science can help. There is other techniques that are needed to fuse information that occur from different kinds of sensors and data sources. Um, One of the key challenges here is how can we represent the real world information into a form that is tractable for learning and other applications. That is the first challenge from a representation standpoint. Again, our community has developed different kinds of methods, especially dimensionality reduction techniques, using optimal wavelets to properly capture and extract features. Graph theoretic approaches have been done. Just to lay a few quick examples from our own experience, what you're seeing here on the screen is a micrograph of a 3D printed surface as printed form. And we can actually come up with a graph representation of this that can be used to characterize the surface evolution during the post-processing processes employed for finishing these 3D printed components. And you can actually be a little bit more simpler. Instead of looking at complex scenarios, you can actually be looking at time series data. And the challenges there come to how we can compress this information or reduce the dimensionality of information so that the enriched features can be used for making inferences about the process. And again, methods have been used for reasoning, using active learning, sequential experimentation techniques. Our community has also looked at forecasting as well as prognostic approaches for manufacturing. Of course, we have at least 30 years of work, especially as a QSR community in diagnostics, and also looking at forensics. And recently, there has been significant thrust in looking at control, security, and adaptation through the advanced AI and data science approaches. And these are just some facets of things that our community has looked at. But talk about what I have been doing in this context. My group has been looking at combining some knowledge about manufacturing processes to address some of the quality as well as productivity issues in both manufacturing process and systems, especially through the use of data science and AI approaches. And the manufacturing domains, we have looked at mostly precision manufacturing and recently additive manufacturing as well as material synthesis. And in terms of methods, our group has looked at different kinds of time series data, especially combining multi-channel and multimodal data, and more recently looking at images as well as other forms of data, essentially from industrial data loggers. And in this particular talk, I will restrict my presentation to address three different challenges. The first challenge is something that is encountered at the manufacturing systems level. Second is more at the what we call as the product level, and third is at the process level. So system, product, and process. And if you can think about the industrial sectors where each of these problems have been taken, the first one is mostly in the high volume automotive manufacturing. The second is mostly in a custom manufacturing environment where you are creating a very high value product, but you don't have lots of components to learn from. And third is what we call as a high-tech industry. So essentially, it's probably high volume or low volume, doesn't matter, but you have to deal with components that require and demand very high levels of precision as well as functionality. So these are the three different industrial sectors and three different what I call as scales from which we can look at it. In the first case, the prognostics and asset management in the manufacturing system, I will present a challenge that involves addressing the question of how to fuse information collected across the plant to improve the reliability of the entire system. And second case, I will look at how can we detect defects in a custom manufacturing environment where you don't have full information about what kind of defects occur a priori. And third scenario, I will look at, again, detecting changes at very incipient stages so that we can avoid some of the quality problems and even minute level quality problems that occur in high-tech industry. And for full disclosure, I think all these problems have been addressed by other members of our community. But what I will try to do is to present my view of what I see as major challenges and some of the results that have come up from our approaches without getting into the nitty-gritty of any of these approaches during this presentation. So to give a quick start, I will talk about the first problem. And many of us have worked in automobile assembly, but to set the stage for describing the problem, I will just run this following video. I'll skip some of the things. So everybody can see this. I hope you can hear the video and see the sound. As you can see here, when you assemble, you're assembling several components every hour. And the assembly takes place over multiple stations. And the material moves, as you see here, between stations through different means. And typically in an automotive assembly line, you have what is called the main general assembly. And there are a lot of these sub-assemblies that make the complete product that we actually see. And each sub-assembly is can be thought of as very diverse manufacturing system. Some sub-assemblies are highly manual and some others are completely automated. And each sub-assembly has about 10 to 12 stations where you can have these stations in sequence, or they can be non-sequence, as you can see here. They may be linear or non-linear. So essentially things in terms of simple queuing, it actually presents some interesting challenges there. So you can have re-entry and so on that people need to deal with. So in all this, the major challenge here is when something fails, it can have significantly more influence than what that particular station affects by itself. Let me repeat. A simple fault in a particular machine has much more serious consequences in terms of affecting the productivity across the entire plant. So this is a major challenge for the automotive industry. How can we make sure we address these issues of machine breakdowns? And to address this, there have been a lot of thrusts. And in the last 10 years, there has been a lot of effort to deploy what are called plant floor information systems, or PFS, for automation and control, and using the data from this PFS for improving the availability as well as overall efficiency of your entire plant. And these plant flow information systems are growing very steadily across the world. The market is growing at a very healthy rate, and it is expected to reach 300 billion plus in the next 4 to 5 years. The typical examples of plant floor systems include all these PLC controllers, SCADA systems, and DAC systems, and you find a lot of them in the plant. If you go to any automotive assembly systems or most of the automation or automated manufacturing systems, you see this PFS system in some form or the other. Alongside, there has been significant introduction of these manufacturing execution systems, or MES technologies, and they are growing at 20%, but they are not necessarily at the same level in terms of the market penetration as PFS, but nonetheless, MES systems are growing very, very fast, and they also provide some additional data. And not the least, these embedded sensors and IoT are starting to make a serious growth in the manufacturing industry. They're growing at over 40%. The rate exceeds the rates at which the MES as well as PFS systems are growing. But their level is nowhere near that of PFS. But these are something that we need to be aware of, and then develop methods that can take advantage of all these diverse data sources, especially the amount of data that they generate of different kinds from different sources. If they are used well, they can be used to predict faults before they occur, so we can prevent them. And also we can learn from the modes in which they fail, so that we can address the failure before they even happen. We are not even preventing them, but we are actually redesigning or readjusting the system so that some of these modes get completely trapped. And there have been studies that showed that we can actually reduce the maintenance and inventory cost by 50 to 20% if we can predict the impending faults, and then we can actually improve the yield by doing so. But the challenge is remains much more than what we have been able to provide in terms of solutions, especially in the manufacturing community. Especially when we are looking at completely interconnected manufacturing systems. People are talking about distributing various manufacturing tasks across the entire enterprise. So they are nothing more or not significantly different from some of these smart grids. If a failure occurs or fault occurs at a particular point, it can literally black out the entire system. So that is basically the gravity of the challenge. And there have been some recent efforts to address this, and we made a particular foray, and we applied it to a 20 machine automotive assembly line that you are actually seeing here. It actually, it's a sub-assembly. It has some manufacturing machines through which the part goes, and it actually produces about 120 components. It's not the full cars, but 120 components about an hour, in every hour. And in a shift, you have a few thousands of components produced. So if there is a failure, it will have a serious ramification on the entire production plant and even beyond. And the approach that we have taken, we call as manufacturing system-wide balanced random survival forest, or MBRSF. And the approach is very similar to many of the survival models that are used to predict failures. except that we took advantage of some of the recent developments in non-parametric methods and tried to use some of the knowledge in terms of how these different machines and processes are connected to each other to develop the state space that can be used for training these models and thereby predict the faults. And more than the method, the results are much more revealing. What we have what we see in this graph is a comparison of the prediction errors for basically errors for predicting faults using the method that we developed with some of the standard methods. The Kaplan-Meier is considered as the baseline, the Cox proportionality hazard method, as well as general random survival forest methods. As we see here, even for about half an hour, the errors for predicting faults remain very flat. What it means is we can actually design methods using the data, just the plant floor information system data, to predict a fault at very good accuracies, almost half an hour ahead. So this actually can be extremely helpful. And then to our knowledge, the data science community has not begun to harness some of this information for life prediction applications. And I think this is something that we can look at it and then improve it even further, especially in terms of predicting for even longer time horizons. So what we try to do is, can we actually predict faults up to a shift ahead? And what kind of prediction accuracies we get. And as you can see here, the integrated Breyer score, or IBS, it's kind of a surrogate for prediction errors. It shoots up as we go beyond half an hour. And the problem that we get to see is we are purely using the historical failure patterns of various machines to learn how the machines will fail in the future. We are not using any of the state information of the machines. So we probably can improve this long-term accuracy significantly more by using some of the state information, especially by taking advantage of these IoT technologies. But even so, the prediction accuracies at long time horizons, they seem to be of the order of the prediction accuracies that we see with other methods, even within half an hour. So I think this method has promise, but we need to be a little bit aware of the new data sources and how it can further improve the performance. And the other idea that we had when we were actually working with the data, especially with our sponsors, is people develop these prognostic methods, but industry cannot use them because they don't have an idea of how accurate it is in actually predicting an impending fault. Because if you look at most of these survival models, what they predict would be basically the probability distribution of your hazard, especially what they call as hazard function. And how can we use that for predicting the actual faults? We kind of developed a visual techniques. So these are some of the things that we as a community can do beyond providing these predictions. And also we can come up with graph-based methods to infer the results. It's not just okay to say that, okay, the machine is going to, there is a good chance that machine 10 will fail in the next half an hour, but also we can probably tell why is it so. So before we get into the physics, even with the historical failure patterns, we can probably say that, for example, here, the failure of machine 8 will have an implication of how the machine 11 will fail, and so on. And I will not get into the details of the color coding, but we can look at the so-called the causal mechanism that takes place for the failures of these machines, especially by analyzing the data, just purely the historical failure data from the machines. And this data is available in almost all automated manufacturing plants. And we can probably look at coming up with data science challenges with which we can improve the accuracy as well as inferences on the failure patterns of these machines. And again, as I mentioned earlier, this doesn't take advantage of the recent growth in IoT as well as advanced smart sensors. By including them, we can go one step further in providing more reliable long-term solutions for the failure patterns. This is one problem that I would like to present to our group. The second is more at the custom manufacturing level. And people talk about 3D printing. And what I want to do is to talk about the potential of 3D printing. And of course, this is a very fast growing technology. I would like everyone to spend some time listening to this if you have not done so.
Work together perfectly. If they don't,
this is about a 3D printing group that actually address some of the safety critical components for the space industry.
Cheaper, quicker alternatives to building spacecraft. And here in LA, I found a startup trying to solve all of those problems in the unlikeliest of ways by 3D printing rockets. This is relativity space.
Existing rocket bits are not 3D printed. What is the advantage of 3D printing? A lot of it, from our perspective, is flexibility. Then the traditionally factories are made of tons of fixed tooling. Then very expensive, very hard to change, then where you have to retool a factory in order to make a new product or even change the product slightly. For us, we can change all of that in software. So it's digitizing the manufacturing process and providing that flexibility, where if you push new code to the printers and the hardware on the factory floor, you can actually make an entirely different product without changing anything in hardware.
So essentially, the idea here is we can actually 3D print some of the high-end one-off components, which are highly valuable. And as you can imagine, we need to get them right. Any quality issues can have serious ramifications, not just in terms of the issue of productivity and then bottom line, but also it can have very serious safety and other issues. And again, data science can offer significant solutions. And what you're seeing in the screen is basically a high-speed camera image of a particular 3D printing process, very similar to what they are using in the previous slide. You have a nozzle where you are depositing the material, and you have a laser that actually spot melts some of this powder onto the place, and it creates layer by layer very custom products. It's actually a directed energy deposition process that we talk about. And we created what we call as a smart manufacturing platform or smart hybrid manufacturing platform, where we can collect different kinds of data during different stages of making these kinds of products and use the data for quality monitoring. In fact, we can use while the process is running, we can collect vibrations of the machine, the forces these powders exert on the surface as they are being deposited, the acoustic emission that gets released, and together they can be used to predict the actual microstructures using advanced methods that we have in hand. And if there are any kind of microstructure anomalies, such as those that result from excessive heating at a particular point, or differential cooling rates and so on, we can actually track them and detect them in situ. And also, we can actually study the process faults. Actually, as the material is getting deposited, we can track how the particles are growing. And one of the key challenges, especially those of us who may have looked at welding, which is very similar to this process, is the challenge called spatter. When the spatter occurs, it creates a lot of these quality issues. And there have been many ways in which we can reduce it. But if you're creating one-off components, it's hard to learn the process recipe that will minimize this spatter. So how do we develop methods on the fly? And so there is lots of interesting opportunities to address quality challenges in these processes. How can we master this process? How can we optimize the process with minimum experimentation? And then how do you reduce defects as well as increase the throughput? So there are interesting challenges in the smart manufacturing area too. And what I will talk about is the issue of how do you use some of these images from these types of high-speed cameras, as well as in situ imaging systems that are becoming more and more prevalent in the lab settings, and they are being considered for niche industrial applications. But the challenge here is how can we use the data that these instruments provide for addressing some of these quality challenges. And the quality challenges, I think, are extremely important in the additive manufacturing domain that I am laying out here. A defect concentration remains a major challenge. This is because in many cases, especially if you're introducing new materials or trying to create a new variant of a product, it's a challenge to create a repeatable print that has reliable quality. And too many anomalies, and then effects are very confounding. More importantly, we don't understand the physics of this process in its entirety. And therefore, people are seeing new anomalies all the time. So in the materials parlance, people are looking at autonomous materials discovery. Whether they're discovering new material or not, people are actually discovering new kinds of defects in the products. And what you're seeing in this right-hand side are two different kinds of defects. One is balling effect, and here and there you have pores on the surface. How can we detect and track them using some of these in situ as well as ex situ instruments? So that actually is an interesting challenge. But we need to deal with some of the problems that you face whenever you have some of these in situ instruments. They're not in a very ideal locations for taking measurements. So they contain lots of noise and significant uncertainties, because you cannot always go back to the same location with very high precisions. And more importantly, you don't have many products. You cannot do lots of experiments to see these defects and minimize them and so on. So how can we characterize, identify these defects? Remains a major challenge. And more importantly, since you don't have many primitives, you don't have access to a very rich labeled data sets that captures all these defects in a very integral way. In fact, the largest one that we have has about a few tens of thousands, but they are very limited compared to the diversity of the conditions in which these processes actually are carried out. So we need a better way to learn these defects and identify them compared to using brute force deep learning as well as other supervised learning approaches. Alternatives, as our group sees, are looking at unsupervised or active learning approaches. Just to give a quick overview, if you look at most of the conventional machine learning, it is passive. So essentially you're looking at showing millions of, it's equivalent to seeing an image, basically a photograph of a speed sign, and then making the computer to learn to detect the speed limits in a particular segment of a street. So essentially you can show millions of photographs in different ways. And then based on that, you can actually have the camera learn about the speed limit so that you can adjust the speed while you are moving an autonomous car. But for manufacturing and other applications, obtaining each photograph is equivalent of performing one experiment. And most of these experiments tend to be extremely expensive. And one way to do it is to cleverly choose the experiments so that you can actively seek to learn where to run the next experiment based on what you have seen previously. And this is basically belongs to the idea of active learning. And the idea here is you are running the experiments. Based on the experiments, you're learning and then determining where the next setting needs to be. And it's part of the sequential experimentation strategy that our community has been working on for several decades. And then we have some of the doyens of this amongst us. And by doing so, it can help reduce the number of iterations, and it will help explore new regions of the input space and deal with some of the surprising outcomes that can emerge in these kinds of contexts. Alternative approaches to identify the key patterns in the input without having prior knowledge about whether these labels mean anything in terms of defects. So learning the patterns or learning to identify the patterns that are interesting in itself can be a major challenge and contribution here. So that deals with the realm of unsupervised learning. And our group has developed some unsupervised learning approaches where you can look at autonomous image segmentation that doesn't require any kind of tuning. And you can achieve very high precisions in terms of identifying defects in additive manufacturing and other scenarios. And such methods can be used even not just for detecting defects, but also can track their evolution under different conditions of the process. We can again develop techniques to perform real-time monitoring of these defects based on some of these fast-moving high-speed camera images, as well as other in situ measurement systems. The idea is, can we generate through our experiments more labels by which we can more accurately predict some of the defects as they occur in some of these additive manufacturing scenarios. So that is one other challenge that may be interesting. And in the remaining time, I'll try to quickly present one more challenge very quickly, which is at the process level.
Autonomous materials discovery
This
is a challenge for current
combines
machinery.
materials and the
The
process
research
here.
is an important step toward practical and fast material discovery. The smart hybrid machine combines additive manufacturing and machining. It uses lasers, metal powders, and heat treatment to modify the structure and properties of the created materials while collecting data about the material. This process can be automatically controlled using a computer. The computer uses code to create parts that can be simulated and verified by the machine before printing begins. The synchronous use of the high-speed camera and other instruments allows for faster data collection, which will speed up the discoveries of material properties. Around 1 gigabyte of data is generated every minute by the machine. This data, along with the discoveries from the machine.
So some of these smart machines are becoming more and more popular. And for high-tech industry, this can be of extreme relevance, especially to detect anomalies in their very incipient stages. What you see here is a CMP process, a chemical mechanical polishing process that many people from our community has worked on. Essentially, are polishing it very similar to the way you grind a surface, but at a very high precisions. What you see here is one of the components that got polished to what we call as specular levels, that is optical finish. The surface roughness is 1 nanometer. So in other words, the average variation of the surface profile is about 1 nanometer. 1 nanometer is basically about 100 to 1,000th of the cross section of a human hair. So it needs to be very precise. And to do that, the industry actually does a lot of in situ monitoring of the process integrity. Because lots of things can go wrong in a high-tech environment. What you see here is a small version of this polisher, but it's equipped with a wireless vibration sensor. And what you see here on the screen is the data that got collected from this machine. Part of the data was collected when the machine was producing good polish, and part of the data towards the end was collected when the machine was producing a bad part. And since it's the end of the talk, I'm going to ask a quick question. Up to what time the signals were coming from good process, and at what times the signal was coming from the bad process. But purely looking at the time series, it's hard to tell. But if you were to guess, you might say that something may have gone wrong at 4,000. But in reality, things actually went wrong much earlier, near 3,000 mark itself. And up to here, the product did not have any scratch. And after the second half, when the polishing was happening, you're producing what we call as micro scratches on the surface. And detecting them using simple techniques is not easy. And several of the conventional as well as modern techniques cannot detect this change very easily. It takes several milliseconds to a few seconds before you can detect this fault. By the time it rolls over, a few seconds means you're actually creating equivalent of 1 meter long scratch, which means the entire wafer that you're producing needs to be scrapped. So you need to be able to detect within a few milliseconds so that you can salvage or at least rework to avoid some of these failures to occur. And again, the problem with convention techniques is the data that you get from these processes tend to be transient. You basically have variation of the signal patterns, where for some time signal amplitudes have a particular pattern, and for other times it has different time frequency patterns. So these varying patterns are hard to capture and then be able to detect. There are some mixture of Gaussian type methods. There are many different methods that we can come up with to capture this transient characteristic of this data and improve the process prediction. And we can actually significantly improve on the times, basically in terms of ARL1, to detect some of these faults. Again, lots of interesting opportunities exist in dealing with some of these transients in the data sets. So with that note, I would like to summarize today's presentation. Essentially, we have been witnessing a lot of advances in quote-unquote AI, mostly data science, to address smart manufacturing for Industry 4.0. And people are really talking about AI for manufacturing in a big way across the world. And there are facets to data science just beyond machine learning that can be applied to smart manufacturing. And I hope I was able to convey some glimpses of the challenges that we encounter at different levels, especially in 3 different contexts. So with that, I would like to thank QSR for giving me this opportunity to talk to you. And I hope some of the material has been helpful. And at this point, I will be glad to take your questions. Again, thank you so much.
Thank you, Professor Bhagapannam. It's really an informative talk. And you packed a lot of contents in this 60 minutes. So let me first ask our audience if they have any questions. Okay, all right. So if I do have a question.
Sure.
Yeah, so you actually presented the main area. One main area is manufacturing of automobiles, and the other one is additive manufacturing. So yeah, so yeah, let me ask Ranjing's question first. Ranjing has the question. His question is, how does the heterogeneous failure mechanism change the model structure of the random survival forest? How the rebalancing of samples changing the structure of the model and the interpretation of that?
Okay. So let me try to understand the question. Essentially,
yeah, he asked the 2 questions.
Yeah, the first one is the heterogeneous failures, right? That is very important.
Right. There is a heterogeneous failure mechanism change the model structure of random survival forest.
Absolutely. In fact, this is a very important challenge which we had to grapple. A machine can fail due to different kinds of problems. Essentially, one could be human related, the other could be even material related. Even there can be different ways in which the problems can occur. So the prediction model may not necessarily be the same for predicting each modes of failure. I believe that may be the nature of the question. So how do we deal with this? What we have done is we basically relied on some of the prior work that was done in University of Michigan in dealing with similar data sets from the automotive companies. And then we had been working very closely at that point with one of the leading automotive manufacturers to both acquire the data as well as work with the data. And the key point here is, although there are about 170 or more fault codes, that is 170 different ways in which a material can fail or the machines can fail, there are essentially two different kinds of failure patterns. Ones that take place on an average of every 20 seconds, that is short-term, very quick failures. And second is what we call as serious and more than 20-second time interval failures. What we have done is we kind of eliminated the short ones, which probably don't have so much of an influence, but focused on the second category, and all the fault codes that belong to the second category was grouped into one set. The simple reason is lack of sufficient data to train for each failure mode. So the model seems to work very well regardless of the failures or the specific type of failure mode. That's a very good question. And the second question is more related.
Second question is how is the rebalancing of samples changing the structure of the model and the interpretation of that?
Yes, actually, the rebalancing was done using a method that we had been working on. A lot more needs to be done in that fashion, but our rebalancing method, again, we are looking at what we call as aggregated data. So we are not training the data multiple times. Once it's trained, we are actually using the same model for making all kinds of predictions over 2-year time interval for our testing. That seems to be working okay.
Okay, yeah, so Anshan also said that, of course, he thanks for the great presentation, and she asked, well, the QSR community members have been working on data analytics and the predictive analytics, but it is challenging to link predictive analytics to decision-making, such as automation, control, and maintenance operations. So she wonders if you have any comments on that.
Sure. Actually, in fact, decision-making and control is not my major domain. Mm-hmm. So I cannot get into the depth of the methods that need to happen. But there are lots of what we call as prescriptive analytics as well as control theoretic approaches that can take advantage of these predictions. Just to give an example, I work with one of my colleagues in electrical engineering. He is very well known in the area of optimal control, Professor P.R. Kumar. And he actually looks at adaptive control theory. In the last few years, he is very excited about the possibilities for improving the quality of a manufacturing operation by closing the loop by use of predictive analytics. So according to him, we can develop what we call as anticipatory control methods and better adaptive control methodologies through the use of some of the techniques that our data science community can provide. Again, I'm not the expert in that area, so this is based on my interactions with my colleague. I hope that answers some of the questions that Inshin has.
Okay, yeah, so I think you answered her question okay, well, pretty well. So I do have a question of my own. Yeah, so you asked, you talk about automation, manufacturing industry, you talk about additive manufacturing. I think they have, you mentioned they have different challenges, but I wonder if all this has some common theme or common technologies or data science knowledge skills that can link all these different industry together. Maybe not just a little bit above the scale of for example, some common, you mentioned active learning, which can be used, I believe, in both. You mentioned it used in additive manufacturing, but can it be used in automation? So I'm just wondering if there are some commonality in the skills in these different applications.
Answer to that question is probably yes. It all depends on how we are obtaining the data and what kind of problem that we are trying to solve. One of the things that I'm seeing in the manufacturing industry is they're getting excited not just about AI, but also the power of imaging techniques. So these cameras are becoming extremely cheap, right? To give an example, the cell phone camera that I have is more powerful than the $250,000 camera that I happened to buy when I was starting my career. So some of the CCD cameras that I had to buy for my experimentations, both as a grad student as well as early career researcher, they are inferior compared to our own cell phone cameras. So the prices have come down. Okay. The power has increased so much. So the industry has seen this. So the advances, this fast and high resolution images present in terms of dealing with high dimensionality, dealing with location, noise, and so on that I outlined, that seems to be a common theme that that basically kind of transcends any manufacturing domain. So that's one thing that I can think of. I'm sure there will be a few others that are common across various manufacturing industries.
Yeah, okay, yeah, very useful. And yeah, I think in many applications, the data acquiring become cheaper and cheaper, but sometimes the acquiring of the effective data is still a question. Yeah, so thank you. All right, so if there is no any other questions, let's end this webinar, and let's all thank Professor Beckham to give us this wonderful talk. Hopefully it will enrich our little bit boring times in stay-at-home situations all these days. And I hope everyone stay healthy and safe. And we hopefully can all get out of this period safe and sound. Okay.
Well, thank you so much, Lily. And then
thank you. Okay, so thank you all for participating in this webinar. I will end this session. So take care. Bye-bye.
Thank you. You all take care. Bye.
Bye.